Yesterday we did experimental probability. Today we're going to do theoretical probability. So by the end of the class, I need you to know the difference between the two and then how to actually do them. Experimental probability, somebody is physically doing something to get you data. You're going to be given a set of data that somebody got from doing some sort of experiment and you use that. Theoretical probability is different. Theoretical probability measures the likelihood of an event based on mathematical reasoning and knowledge of a situation. Okay, so here's what that means. Theoretical probability is what should happen. Hypothetically, what should happen. Experimental probability is what does happen when someone actually does it. Okay, so the easiest way to explain that is in a very basic terms. If I had a penny and I flipped it, what's the percent that I should get heads? 50. That's theoretical. Experimental is me putting a penny on Alyssa's desk and saying, flip that 10 times. She doesn't necessarily get heads 50% of the time, right? It's an experiment because she's doing it, okay? So theoretical is what should hypothetically happen before I actually do anything. Experimental is what does happen when I do something. So the first example says you have numbers in a hat labeled 1 through 15. If you randomly choose a number, what is the theoretical probability that you get a multiple of 3? There's a lot happening in this problem, all right? It's not experimental. Experimental would be having a hat with 15 numbers in it and walking around and asking you to pick numbers out and me recording that information and then me finding the answer, okay? This is just hypothetical. So if I'm thinking about the hat itself, those are the numbers in the hat. All right? Of those numbers, I need to figure out which ones are multiples of 3. Which are multiples of 3? 3, 6.
9, 12, 15.
Multiples of 3 start at 3. And then 3 plus 3 is 6. Plus another 3 is 9. Plus another 3 is 12. So the green highlighted numbers are multiples of 3. So now what I'm saying is, what is the probability of getting a multiple of 3? So the numerator would be the number of numbers that are multiples of 3. 1, 2, 3, 4, 5. There are 5 multiples of 3 out of the total number of numbers. How many numbers are there? 15. We know that we should reduce that if we can. So yesterday we talked about how you could go to your graphing calculator and do 5 divided by 15, math, enter. So I'm going to change that to 1/3. That is a hypothetical situation because I physically did not pick names out of a hat. Somebody didn't pick names out of a hat. This is just what should happen. That's theoretical probability. So the next example, which I believe is on the next page of your packet, toolkit page 2, says you roll a standard number cube, which is a fancy way of saying a dice, right? Like you roll a 6-sided die. What is the theoretical probability you get a factor of 6? This is not an experiment. If this was an experiment, I would have a list of results. Like I would have like 2, 3, 7, 6, 1, 2, like actual outcomes people got when they rolled a dice. That's experiment. This is theoretical. I didn't roll a dice. I'm just thinking about the dice. The dice has 1, 2, 3, 4, 5, 6 numbers on it. And I need to think about which of those numbers are factors of 6. To be a factor of 6, you do 6 divided by this number, and you get a whole number as the answer. Okay, so let's think about the number 1. Is 6 divided by 1 a whole number? It is. So 1 is a factor of 6. Is 6 divided by 2 a whole number? Yeah. So 2 is a factor of 6. Is 6 divided by 3 a whole number? Yeah. So 3 is a factor of 6. Is 6 divided by 4 a whole number? It's not. 4 is not a factor of 6. All right, what about 6 divided by 5? Is that a whole number? 5 is not a factor of 6. What about 6 divided by 6? That's a whole number. 6 is a factor of 6. Factors of 6 are numbers that can divide into 6 evenly. All right, so here are my factors of 6. So the question is, what is the probability of getting a factor of 6? So it would be the number of factors of 6 out of the total number of numbers. There is 1, 2, 3, 4 factors of 6 on the dice out of 6 total numbers on the dice. 4, 6. And then I'm just going to check that. 4 divided by 6, math, enter, enter. So 2/3. So my answer here is 2/3. My thing's frozen. Yep. All right, the next example says making predictions. If you roll a standard number cube 100 times, how many times would you expect to roll a factor of 6? So I'm going to take the times I would expect to roll a factor of 6, 2 out of every 3 times. Or you could use 4 out of 6. It doesn't matter. 4, 6, or 2/3. They're the same thing. Equal to another fraction. Now remember, these are the factors of 6. These are the totals. 100 is a total. I don't know the factors of 6. So I'll call this an X and this a 100. The totals go in the same spot. How do we solve a proportion? We cross multiply. So we're going to cross multiply this. 2 times 100 is equal to 3 times X. And then we're going to divide by 3. Of course, math hates me and wants to keep giving me this atrocious number. All right, so X equals 66.67. However, we talked yesterday about how we're going to round that because I can't roll the dice a portion of the time. So you're going to round this either way. I would accept 66 or 67 as the answer here. You don't have to have both. You can pick one. You okay with that? All right, so I'm going to have you do quick practice on theoretical probability in your workbook. I think it's on page 3. So these are the bottom 2 problems on the first page of your workbook. We did 1 and 2 yesterday. Now you're doing 3 and 4. The problem itself says a bag contains letter tiles that spell the name Mississippi. So picture like a bag, and in that bag there is one tile that is an M, and then there's a tile that's an I, and then there's another, then there's an S, and then there's another S, and then there's another I, and then there's a P, and then there's another P, and then there's an I. Is that right? N-I-S-S-I-S-S-I-T-E-I. I'm a little off. There's 11 tiles in there. Okay, so there's multiple S's. There's multiple I's. So 11 total tiles. What I'm looking for you to tell me is, what is the probability that I reach in there and I pick out an I? What's the theoretical probability? I'm not actually doing it, so it's a theoretical. What do you think? What's the theoretical probability that I reach into that 11 tile bag and I pull out an I? 4 out of 11. There is 1, 2, 3, 4 I's in the bag out of a total of 11 letters. So the theoretical probability is 4 out of 11. What about S's? Another 4? Let's see. 1, 2, 3, 4. out of 11. Both of these are called theoretical because nobody had a hat with those letters in them and actually picked out letters. It's theoretical. It's what should happen based on the name itself. Nobody actually ran an experiment. All right, so I want to finish today's class with just making sure you truly understand the difference between experimental and theoretical. All right, so this is on page 2 of your toolkit. Says Jason spins an 8-sided spinner 10 times. He lands on 1 time, 2, 3 times, 3, 2 times, 4, 1 time, 5, no times, 6, 1 time, 7, 2 times, and 8, no times. That's kind of confusing. So here I have the data. Okay. Jason spun the spinner and then he wrote down what he got. And then he spun the spinner again and he wrote down what he got. And then he spun the spinner again and he wrote down what he got. He did that 10 times and this is the numbers he got. This is his data. So anytime it asks you to find an experimental probability, you want to use Jason's data. But if it says theoretical probability, I don't care what Jason did. I want to think about the device. How many sides does the spinner have? Think about what the spinner looks like. Jason spins an 8-sided spinner. Okay, so when it says experimental probability, look at Jason's data. When it says theoretical probability, look at the spinner. You see the difference? All right, so let's see. The first one says, what is the experimental probability that Jason will spin a 3? I'm going to look at his data. Here's Jason's data. Here's his experiment. How many times does he get a 3? 1, 2 3s in his experiment. So it would be 2 out of, what would the denominator of the experiment be? 10. The experimental probability of getting a 3 would be 2 3s out of 10 numbers, or 1/5. What's the experimental probability of spinning a 2 on the next spin? Experimental, I want to use his data. Experiment is Jason's data. How many 2s are up here? 1, 2, 3. 3 out of 10. Then when it switches over to what is the theoretical probability of getting a 3, I don't care what Jason did. I want to look at this. If I spin this spinner right now, how many numbers on the spinner are a 3? Out of a total of 8. So the experimental probability of getting a 3 is 1/5, but the theoretical is 3/8. 1/5 is what he actually got. 1/8. I'm sorry, I didn't need to write one number on the spinner out of 8. So he actually got a 3 1 out of every 5 times. But hypothetically, I thought it should have been 1 out of every 8. Right, if this is an even spinner, 1 out of every 8 would be the theoretical probability. What is the theoretical probability that Jason will spin a 2? So I'm looking at this. How many 2s are on the spinner? 1 out of how many total? Experimental, use the data. Theoretical, use the device. So I just kind of jotted this note off to the side here. Experimental probability, use the given data. So if I want to find the probability of some event A happening, I'm going to look at the data for the A's. The numerator would be the number of A's in the data, and the denominator would be the total numbers in the data. If I want to find the theoretical probability, I'm not using data. I'm just thinking about what should happen. So I'm going to use the device. Data versus device. What do you think? Okay, tomorrow when you come in, I will not be here, okay? So you are going to have 2 assignments. They're written on the backboard. They'll be there tomorrow. The sub will explain them to you. They are on Canvas too. It will be an Ed puzzle explaining complement probability. It's really short. It's 2 examples at the end of this page of your toolkit. So it's a really quick Ed puzzle, okay? Embedded in the Ed puzzle will be checks for understanding. So you try an example and pick the answer. That will be graded for accuracy. So if you don't like your grade, you can watch the Ed puzzle again. It's really short. The second activity will be practice, but it's on Canvas so that I can check the answers, right? So there'll be a link on Canvas for you to work on, and that will be due by 11:59 tomorrow night, so that if you don't finish it in class, it's still open. You'll have 5 attempts at that. Tomorrow I need you to bring headphones so you don't hear my voice 22 times. You'll just hear it once in your ears. Does anybody have questions for me? All right, you don't have any homework for tonight, except make sure you bring headphones in tomorrow so that you can use them for tomorrow. You'll have 2 assignments for tomorrow, an Ed puzzle and a Canvas.
Just reminding, not going to be here tomorrow.